But the very last thing we left off talking about on Wednesday was Zaitsev's rule, and that deals with the regioselectivity of the elimination reaction. Remember, Zaitsev studied these reactions, and he determined that the most substitute alkene is the major product. Okay, so this happens when we have an alpha leaving group with 2 beta carbons, right? So when we eliminate, we can imagine taking either of those hydrogens from either of those beta carbons, okay? And it's the most substituted alkene that's going to be the major product. So you can see here, this is a tri-substituted alkene. 1, 2, 3 substitutions on there. And over here, this is actually a mono-substituted alkene, just one group coming off of that alkene. Okay, just look at the actual alkene and how many groups are coming off of it. We got 1, 2, 3 here, and we only have one group coming here. So the last thing we talked about was Y. Y is the most substituted alkene, the major product. And I mentioned it's the most stable, okay? And I said how alkenes, just like radicals, just like carbocations, everything wants electron density, and that includes alkenes, okay? So the more alkyl groups we have on there, the more electron density we have to donate, and so therefore we have the most stable. Now you can see I have drawn each of the possibilities for the different alkenes in terms of their substitutions, right? This guy over here was tetra-substituted, so we can label him tetra-substituted. This guy is tri-substituted. All of these are di-substituted, and they are ranked appropriately in terms of their stability. Anybody tell me why these might be separated as they are in terms of the trans being more stable than this guy being more stable than the cis? Anybody have an idea? The answer is because everything wants to be as far apart as possible, right? Here in the trans, these groups are as far apart away as possible. In the cis, they're closer. Here we get to have a 120-degree separation in those bond angles. We'll actually see that that's important too. Okay, so it actually goes trans, and then the di-substituted on one carbon, and then followed by the cis in terms of stability. This guy is mono-substituted, and this last guy has no substitutions. No substitutions. Okay, so again, it was the tetra-substituted that was the most stable because it has the most alkyl groups donating electron density to that alkene, because that's what the alkene wants. And over here, the no substitutions was the least stable. Okay. Another reason why the most substituted alkene is often formed is because, again, groups want to be as far apart as possible. Want to be as far apart as possible. So let's look at what happens when we form the multiple substitute alkenes. So for instance, let's say we've got this guy versus this guy. So this is the exact 2 products that we just showed. Okay, can anybody tell me the bond angle right here? What hybridization is this carbon right there? This is an sp3 carbon. So what is this bond angle? It's 109.5. Okay, and again, this was the mono-substituted. Mono-substituted. And this guy, what is he? He's the tri-substituted. And can anybody tell me the bond angle right here? What's the hybridization of this carbon? sp2. So this is a 120 degree bond angle. Okay, so here you can see the carbons get to be further apart because here they are forced to be 109.5. Here they get to be further apart. So again, the tri-substitute or the more substituted groups on the alkene, the further away those groups get to be from one another and the more stable they are. Okay. Another issue with regioselectivity is that of rearrangements. Okay, does this sound familiar? It should, because right, we go through that same intermediate as the SN1, which is again where we also will see rearrangements. So let's take this cool reaction. Okay, we're going to put it in with some methanol. We are going to need some heat to form these products. We're actually going to get 2 different products. We would get this one that we would kind of expect, but we also are going to get this guy. Okay, and it's this one. This guy is our rearranged product. rearranged product. So let's look at how this can form, how both of these products can form. Okay, again, we're talking about the E1. So what's the first step in the E1? E1, just like the SN1, right? Leaving group leaves, first step. Okay, to form the what intermediate? The carbocation intermediate, okay? And so from here, right, we have more methanol in there. And so we could easily just go and deprotonate this beta hydrogen, fold down to give our expected E1 product. Okay? CH3OH2, as we've always drawn, and we had Br minus leave. Okay? But another possibility though, okay, what if we did a ring expansion? Okay, so this is the rearranged product. Remember last time I talked about the possibility of hydride shifts. I also talked about the possibility of a methyl shift. Well, here we're going to have somewhat of a methyl shift. It's just kind of a carbon-carbon electron shift, and as a result it's going to expand the ring. Okay, so I'm going to call it a methyl shift though. So it's literally these electrons that are between these two carbons, they shift. Okay, it's these two electrons. So I'm starting the arrow in between these two carbons because it's starting at these two electrons between the carbons, okay, at that bond. Okay, so that you guys can see what's actually going on, I'm going to count my carbons. 1, 2, 3, 4, 5, 6. Okay, my product is going to look like this. Okay, let's count. 1, 2, 3, 4, 5, 6. Does everyone see? Well, first off, let's write the whole reason why this happens. We get a methyl shift, okay, to relieve ring strain. Do you think that cyclobutane is very stable? Probably not. Is it more stable as a cyclopentane? Absolutely. And that's why this takes place. Okay? So you can see here that my electrons were between carbon 6 and 3. Until they were between 6 and 3, but now I have shifted them between 6 and 2. 6 and 2. So, interestingly, which carbon got left out in the cold? Okay, because we started with a plus charge, so we have to end with a plus charge. Where's the plus charge? Again, the electrons were between the 6 and 3, and now they're between the 6 and 2. So which carbon got left out? It's carbon 3. Carbon 3 has the plus charge left. Okay? And so don't forget that we still have these hydrogens here. So when we have more base or more solvent, he can go and deprotonate. Fold down to form the other possible product. Okay? Again, we have CH3OH2 plus Br minus that left. Okay, so this would be a ring expansion is really kind of what we call it, but it's just a methyl shift. That's all that's really going on. Okay, and again, this is done, and we don't form a more stable carbocation technically in the sense of we go from a secondary to a secondary, but we do relieve this ring strain. So in essence, it really is more stable. Okay. All right, now stereochemistry, another important topic. Okay, sorry, last thing. Remember, general rule: if we can rearrange, it will. So be on the lookout for those. Be on the lookout. Okay, stereochemistry. Stereochemistry is very important. And you think, how do we have stereochemistry of alkenes? Remember, we can have cis or trans alkenes. So in elimination, that's what we're talking about, okay? We're not talking about RS necessarily for these elimination reactions. Instead, we're talking about E or Z, or cis or trans, okay? The trans alkene. We haven't used this terminology all that much yet, but the E alkene is the trans alkene. You can see here, E1 reactions are stereoselective. This isn't a buzzword, okay? And by that, there's a choice of different pathways that the mechanism could take, okay? And when we have a choice, we're called stereoselective, okay? And from this choice, we form the E alkene or the trans alkene as the major product, okay? So for instance, if we have this guy, this leaving group right here, okay? if we rotate about this bond right here, okay, we could also have this guy. Not also, it's the same guy. By the way, pH stands for phenyl. I don't know if you guys know that. It looks like this. R. So this is a phenyl group. So my R group is the rest of this over here. And so when we go in with a weak nucleophile, somewhat basic, but weak base as well. Okay, this is a neutral base, definitely not strong. So we're going to undergo E1 and we get two products. We could get this product and this product. Okay. So, which one of these is the trans? The left or the right is the trans alkene, right? The one on the left, okay? This is the trans alkene, also known more commonly, as the E alkene. Okay, so we'll start using E versus Z now. This guy is the Z alkene. I always remember Z because it's Zamzide. I'll write that in a minute. So this is the cis alkene, okay? And just as it says there, form the E alkene as the major product. So this guy is going to be our major, and this guy is our minor. Okay? And so with all of these things that I just tell you though, we have to wonder why. Why? Why is the E alkene the major product? Can you guys guess based on what I usually say? Probably because it's more stable, right? It's definitely more stable. But why? You guys can definitely tell me why it's more stable. Because it's more stable. Why is it more stable? Why is the trans more stable than the cis alkene? Let's think about another underlying factor why everything is, not just electronegativity. You guys like to use that buzzword, right? But the other reason for lots of things, right, is that groups want to be as far apart as possible. Want to be as far apart as possible. Okay, so it's again why for the di-substitute alkenes, the trans alkene was more stable than the cis alkene. Okay, so let's draw this for effect though, just to kind of show us. Here's the trans, or the E. Okay. Here's that big old phenyl group with that methyl. And let's draw all the H's again for effect. H, H, H. Versus the cis alkene. Cis or Z. Okay. Remember, we like the trans. Again, let's show all the H's for effect. 1, 2, 3. Okay, so we can see here, you can definitely already see that these hydrogens for the methyl group are pretty close to that phenyl. So we have this steric bumping here, right? The cis alkene puts groups closer. Groups closer. Therefore, less stable. Less stable. Whereas the trans alkene, right, we don't have that. That's why it's the major product. Okay? The trans alkene puts groups further away. Which is why this alkene is more stable. Okay? So again, that was the E1. Okay, these are E1 reactions. Okay, we go through that carbocation and we can rotate about that single bond. Okay, we can rotate about these single bonds, whether there's a carbocation here or not, and we can form either of those products. And again, we're going to form the trans or the E alkene more often, the E1. E2 reactions are a little bit different. Okay, instead of being stereoselective, again, we have don't have a choice this time, okay? So these guys are stereospecific. So here's a new buzzword, stereospecific, okay? They do not have a choice of pathways, okay? And that's because they need an anti-periplanar arrangement of the proton and leaving group in the transition state, okay? So that's a lot of words. We have to show it. All right, so we have two cases here. Let's use this one. And we have this enantiopure material. We're going to use a nice big bulky base to ensure that we get E2 here. And we get only one product this time. Whoops. The methyl group is here. And the phenyl group is up here. Remember, Me stands for methyl. Remember, if you guys remember that. Okay? So this enantiopure material gives only one product. Okay? So the E, or the transalkene, is the only product. Okay? Versus, interestingly, if we use this guy, where the methyl group is going back here. Again, he's still going to be an enantiopure, but he's a different enantiomer. Sorry, he's a diastereomer. This guy's a diastereomer of the first guy. Okay? Same conditions. And to get E2. Okay, and this time, we get only this product. Okay, so this is the Z alkene, the cis alkene. Only. Again, for each of these, we only get one product. Remember, for the E1, we got both cis and the trans, but the trans was the most stable. So you see the difference between these? The phenyl groups, even if you were using them for like R and S, have priority here. So you can see across the alkene, they're on opposite sides, whereas here, they're on the same side of the alkene. Okay, so we get these two. Well, each reaction only gives one product, and you can see each time it's different. Okay, just depending on the orientation of this methyl, we get a different product. We only get one product. Again, as opposed to a cis and a trans alkene. We only get one. Again, there's no choice here. We only get one. And as it says there, it's because this is a stereospecific reaction due to this anti-periplanar arrangement. All right, so let's try and draw this now. Bottom line is it has to have this anti-periplanar arrangement. So let me try and show you what that looks like. Okay. All right, so we have our starting material with this H going back. It wasn't drawn originally, but it is always there. Okay. Importantly, it says here, it's an anti-periplanar arrangement of the proton and leaving group in the transition state. Okay. So when it says anti, I'm saying literally that the H and the leaving group have to be anti. Everyone see that? In this orientation, in this conformation, they are anti. The H and the leaving group. That's what we're talking about. The proton and the leaving group. Okay? So now when I do this, to do this I had to rotate about this bond. So if I bring that H forward into the plane, what happens to that methyl group? Okay, if I brought that H forward to put it into the plane, that methyl group goes down, but he's still forward. And that phenyl group, what happens to him? Again, I brought that H forward, the phenyl group goes back. Okay, that takes practice. I can do that. I can see it. You might need a model kit to be able to see that. So then importantly then, this bromine was going forward, I pushed it into the plane of the paper. So what happened to that phenyl group? If I push the bromine in the plane of the paper, the phenyl group comes forward. Okay? So now when I have my strong base, O minus K plus 1, 2, 3, 4, 5, 6. So when I have my strong base, okay, we go and deprotonate. And we are all set to deprotonate because the H and the leaving group are anti-periplanar. Okay, if we could see this, okay, if we look down that this bond right here. Okay, what does it look like? Looks like a peace sign. Okay, I've got my H up here, got the methyl on my right, phenyl on my left. Yes, that takes practice, you should be able to see that. But then anti to the H is that bromide. Okay, phenyl is then on my right, and then there's an H that I didn't draw, but he's still there. Okay, so you can see here that the H and the bromine are anti to one another, all in the same plane. Okay, to be anti, you pretty much have to be in the same plane. So, anti-periplanar just means in the same plane. Okay, and it's only because of this conformation that we can then undergo the E2. Okay, so then importantly now, do you notice that both the methyl and the phenyl are wedges? Okay, Me and PH, both wedges. Okay, therefore they're going to be on the same side of the alkene. It's hard to see. I'm giving you guys tips here. Same side of alkene. Okay, so if we could kind of draw this product then, let's draw it kind of in 3 dimensions to see it better. I have an H going back there, I have the phenyl going back there, but then I have this methyl group coming forward, and the phenyl group coming forward. Okay, again, because both the methyl and the phenyl are wedges, so they're both coming at me. You can see it over here too. The phenyl and the methyl are on the same side. If this is like making our molecule, cutting it down the middle to be our alkene, the phenyl group and the methyl group are going to be on the same side of the alkene, and the H and the phenyl group are going to be on the same side of the alkene. Okay? So if we drew this in the plane of the paper, which is what we are used to drawing, it looks like this. Me. Okay? So then conversely then, let's practice again with this guy. He equals that. So then this guy equals, again, we need to put the H in the leaving group anti-periplanar. Okay? So I don't have the H drawn here, but it's right here coming forward. And we need to put the H and the leaving group anti-periplanar. It's not a very good anti-periplanar. There. A little bit better. Okay? Again, they're in the plane of the paper and they're anti to one another. Okay, so in doing that, okay, I push this H back. That phenyl group is going to come forward. And that methyl group then ends up on the bottom, still going back. You can see that? I push this H into the plane of the paper. That brings the phenyl group forward and puts the methyl group down. And then here I push the bromine into the plane of the paper. So that brings the phenyl group forward again. Okay, so then again, when I have my base, K plus, okay, we can go and deprotonate. Fold over, kick off. Okay, let's look at this guy in his Newman projection. Okay, let's look at again down this bond. Okay, he looks like a peace sign again in front. H, phenyl group on the right, methyl group on the left, and then I've got the bromine anti. And then what? I have the phenyl group on the right this time, just like before actually, and then an H in the back. So what's different now is the phenyl and the methyl group between these two. Okay, and that's again because we started with a different configuration at that carbon. Okay, so again, these phenyl groups now are on the same side. Okay, so the alkene we're going to get looks like this. The phenyl groups will be on the same side of the alkene. Okay, because you can see here, they're on the same side. And the H and the methyl, I haven't drawn it, but there's an H right there. They're on the same side. Again, we can see this again because the phenols here both have wedges. And if we drew the H, it would have a dash, and the methyl group would have a dash. So they end up on the same side. Okay? So again, this guy was the trans. And I told you guys this means E-alkene. And this guy was the cis, which equals Z. And so note how I remember these things, and we'll actually go into more detail about how I can tell whether it's cis or trans in the next chapter. But Again, the E equals the trans alkene, and Z equals cis alkene. And I remember this because we have zame, zide. That's how I remember the Z equals the cis, because they're on the same side. Okay, so I've told you again, I've simply told you that we have to have this antiperiplanar arrangement. And again, it's because we have to have this arrangement to do the E2 that we only get one product, okay? We only get one product, stereospecific, we only have one choice, okay? But of course, we have to ask ourselves why. And so this goes back to everyone's favorite topic, the molecular orbital overlap.